Hello, my name is Tyler Bell. I'm working with LeAidan Smith on the XFLR5 Fundamentals of Aerodynamics project for UCF class EAS3101. So to begin, the airfoil we'll be working with is a NACA 2415 airfoil. Our aspect ratio will be 14, our taper ratio will be 1/2, and our root chord length is 2 meters. So taking in all the given information, let's start with just constructing the airfoil in XFLR5. So what you want to do, you want to have your main page of XFLR5 open. You want to go to Module, and you want to go to Direct Foil Design, or Control 1. In here, you can see just a general airfoil given to you by the program. We don't need to worry about it. We can go up into the top and click Foil, and we go down to NACA Foil. It's also shortcut is Alt-N. We're gonna click on it, and we just plug in our NACA digits, so 2415. All right, we leave the number of panels at 100, and click OK. You can see our foil kind of pop up right there. This will pop up to rename it. To save the foil, you click OK. All right, so now our NACA 2415 foil is saved in XFLR5. Actually, let's save this real quick. Let's go to video files. NACA 2415. Go ahead and save. So our project's now saved, and I can continue to save it along the process. So once we have the airfoil here, we need to do an analysis on the airfoil itself. So we're going to click Module. We're going to click Xfoil Direct Analysis. It'll pop up with a window looking like this. And you can do to start. You can start with the define analysis if you want. This will define an analysis at just one Reynolds number. So I have it set to relatively high, like 6. But we can go even lower. Let's just say 3 million. 1, 2, 3, 2, 3, right? And just say Reynolds number 3 million. And off to the side over here, where it says, let's see if I can make that a little bit bigger. Direct airfoil analysis. We have analysis settings. We want to sequence from -5 to 30. Our final wing analysis will be from -5 to 25. However, I found that having that end go a little bit further, sometimes I can get like 1 or 2 extra angles of attack to converge on the wing analysis. So I'll just leave it at 30 for this one. Right? Our step is just 1 degree. So I click Analyze. I see that most everything converged. I'll give a couple that will diverge or unconverge according to XFLR5. You can close that window. And this gives us a graph of our Reynolds number when it's 3 million, right, for this airfoil. We're dealing with a tapered wing here, so our Reynolds number isn't the same at the root as it is at the tip. It's going to be changing. So what we really want to do is we actually want to do a batch analysis. So if you click on Analysis and click Batch Analysis, you'll see here we're going to have Reynolds numbers from 30,000 all the way up to 6 million, right? I obviously have added in some of these and it just saved them. So normally it only goes up to this 3 million mark, and I went in and added everything after it. So, let's say I want to add another one in here. I can either click, insert after and just type in whatever I want, or if I just want, steady incremental steps, I can just keep clicking insert after and just keep doing that a whole bunch of times till I reach a good number. Down here on the bottom, our analysis range, again, we want to do a sequence on our angle of attack, or alpha, from -5 to 30. And we're going to increment it by 1. I'm going to be using 4 threads just to speed up the process a little bit. You can leave it at 1 thread if you have a slower computer, but I'm just going to run the 4. Once you have all this set up, you want to click Analyze. It's going to run through all of it, and you can see all of our different Reynolds numbers pop up on the graphs, right? Close, we can look at the graphs a little bit better. All right, these are all of our different Reynolds numbers and angles of attack. That's all we pretty much need for the airfoil portion of it. So let's just click save again, and we're done. We don't need to touch the airfoil again unless we have any issues in the wing analysis where we have a lot of stuff unconverging or things showing up outside of the flight profile. So then we can go to module and we can go to wing and plane design. Then up in the top, you see plane, click on that and define new plane. We're going to name this plane NACA 2415, aspect ratio 14, taper ratio 0.5. Right, I'm just going to copy this because we're probably going to want that later. So we're just dealing with the wing. We don't need an elevator, so we can click off of that elevator, and we don't need a fin, so we can get rid of that as well. What we do want is we want this main wing to be defined. So we're going to click on define. It's going to pop up a window like this. Our chord is going to be, there we go, 2 meters. This is the root chord. You see it's at Y0. This is our y-axis, so it's 2 right there. And we want our tip chord to be 1 meter for our taper ratio to be 1/2, because it's, tip chord over root chord, so 1/2 equals 1/2. Our offset, we can set that right now. We want this to be 0.5 so that when we're looking at it, it's offset evenly. Both the leading edge and trailing edge have the same angle from the y-axis, just the inverse of each other. Now the last thing is going to be our wingspan. We want our aspect ratio to be 14. So we need to, figure out and do some math to figure out exactly what our wingspan is going to be. Well, you can do the math on your own time. It's not very complicated. It's only, substituting in from one equation to another. And I did it already and found that our span needs to be 21 meters. However, we're just talking about our offset. And since I have the symmetric button clicked up here, I don't want to type in 21 meters here. And in fact, if I do, you'll see that I have an aspect ratio that's twice as high as what I actually want. I have an aspect ratio of 28. What I want is I want to type in 10.5 meters. That'll bring my aspect ratio down to 14, which is what I want, right? However, now that I have all that set up, I have my aspect ratio, my taper ratio, all that's good, my offset's good. My dihedral, I don't want any of that, and I don't want any twist. If I look at the wing, it's completely flat right now, right? We have no 3 dimensions, only 2D. Now if I just click in this little foil section, NACA 2415 will pop up. I do it on both, and there we go. Now we have our airfoil put in there. If you have more than one airfoil, or you want to do multiple airfoils per wing, you can just hit this drop down and open up and select the other airfoils for where you want them. But since we only have NACA 2415, I'm going to leave it at that. I'm going to click save. I'm going to click save again because I can see the wing right here. So now what we're going to do is we're going to do the analysis for the wing itself. So to do this, what we're going to do is we're going to click analysis, define an analysis, and we want our velocity. Our velocity given to us was 50 meters per second. And we want fixed speed, right? We're not changing the speed. We don't want to change we won't fix lift or fix angle of attack because we're going to be changing angle of attack, and we want to see, differences in CL versus CD or CL versus alpha, stuff like that. Now what we're going to do, just to double check it, we're going to click on the analysis tab in analysis definition, and we're going to be using the lifting line theorem, or LLT. This is the analysis method we want to use. We don't really want to be using the other ones right now, and the rest of these tabs we don't really care about. Like on the aero data, if you know an altitude that you're flying at, you can change the density and the viscosity, which also means, you're already gonna know those from your Reynolds number, which you would have plugged in earlier. So that's pretty much fine there. We can click save, and right here it will give you the range of your Reynolds number. So this is kind of how I knew what to do. The other way you could have done it is you could have solved for the Reynolds number at the root and the Reynolds number at the tip, knowing what, using these values, and then you can plug in your Reynolds number and doing your batch analysis that way. We're going to click save though. So now I'm going to change this graph so we can see it a bit better because it's gray on black and it's not going to look very nice. So now we're going to have magenta on black. What we're going to do over here is we're going to we have our analysis settings. Obviously, we're going to want to sequence again, -5 to 25. And for some reason, the little delta triangle shows up as a square right here. This just means we're going to increment by 1, initialize LLT. Everything else should be set up and ready to go. We click Analyze. If we scroll through here, right, I can see that it converges after so many iterations. Now, right at 21, I'm getting converge after 43 iterations, but it could not be interpolated. Some of the issues with this could just be Reynolds number issues, stuff like that. So, let's say all of these Reynolds numbers are the exact same. Let's copy it real quick. And let's go to save everything real quick. Let's go back to the XFoil student analysis, define an analysis. Let's just plug in this Reynolds number where we had issues with interpolation in. Let's click OK, analyze. All right, we got a couple unconverges throughout it, but should be mostly fine. Save it, back to the wing, and let's hit analyze again. Let's just see. So we're still having issues with it. It could just be that this is, outside of the flight profile, something like that. I'm not 100% sure exactly why it's doing it, but we should be fine, and we should be able to get all of our information just with -5 to 20, right? Even if I bumped up the amount of iterations here to, let's say, 500, my current iteration maximum is 200, they all converged. So there's something else going on in the background that, I can't really control. I may not be able to control. Since we're getting, alpha plus alpha induced plus twist of 40 degrees, this may just be having some issues. So if we just hit close here, so now we have our 4 different graphs that we really need. So we have our CD versus CL, or CL versus CD. We have our CL versus alpha. We have our CL over CD versus alpha. And this one right here is saying CM versus alpha. Well, we don't really want that one. So what we're going to do is we're going to change this to our CD versus alpha. So all I do here, you right click on it, go over to show graph and define graph settings. And it'll give you a drop down. Your y-axis you can change. You have all these different variables you can use. Same thing on the x-axis, right? All of these. So you can set up a graph for anything you want using these. But so what I want is I want my CD versus alpha. Where's CD? There it is. So CD versus alpha. Click OK. And there we go. All right, we have our 4 different graphs. If we go over here, we can get some more graphs. You can get induced angle of attack over the span of the wing. You can do induced drag, CL over the span, airfoil drag over the span, and for some reason it's giving me, I have it set up for 2 CLs over span, but the 4 we care about are these 4 right here. And they're useful, right, as they are right now, but they're more useful if we put them in Excel. So to export all this data to Excel, you're going to click on the graph. You're going to right click on, let's say, the CDCL graph, right? Right click on it. I'm going to go current graph. I'm going to hit export graph. Now I'm going to export it to the specific location. Where is it? Video files, right? I'm going to name this the CL versus CD. Just CL versus CD. I mean, I can also throw in like AR14 TR 0.5, right? Do stuff like this, copy that, right? And then we're going to hit save. The other thing too, actually, is you see over here where it says the T1-50, this, when you export it into Excel, will make it difficult if you have multiple wings to be able to determine what column's actually which one. So it is, good practice to rename this to what you're working with. So this is, we'll go NACA 2415. Right, this is our NACA 2415, the aspect ratio 14, TR 0.5, instead of this. This only works because we're also just doing a single NACA airfoil. That's why I'm doing it like this. Obviously, organize it however you want. I just found that when doing multiple wings on the same graph, just having T150, it's not very clean. Makes it more annoying to deal with the Excel graphs. So I'm just going to click OK, and I'm just going to re-export this graph. graph. Nope, exporting as a TXT. We'll change that. It goes CL or CD. Yeah, you don't want to export it as a TXT. You want to export as a CSV. So it's actually an Excel file, not a text file. And then we're going to click OK. CL versus alpha, we'll do the same. Export graph, we'll do CL versus alpha, save, CD versus alpha, export, CD versus alpha. And then the CL over CD versus alpha. Export graph here, CL, and then obviously I can't do the little, I guess I can do it. It was giving me issues the other day with it. Oh, verse. Right, and click. Oh, no, see, name invalid. So what I do is I just leave it like this, or you can do an underscore if you want. Then we click, all right, okay. So that's all the Excel graph or Excel data that we need right now. Let me double check. I'm getting everything. Need to show analyzing and plotting the data. Okay, so now what we can do is we can actually go and open these Excel files. So classes, spring. See, there's a lot of trial and error with some of this stuff. So let's go first with like CL versus alpha, right? Here you can see the name popped up over this column. This column, what I like to do is actually like to drop everything down, bring this to right there, and rename this to CL. So it's actually, you know, keeping with what the graph should be. So this is our CL versus alpha. I'm actually going to change this to a XLSX instead of the CSV. Save it. So now what we can do is we can create some graphs. I'm going to do the scatter with smooth lines. For some reason, my Excel recently has been doing this, so I'm just going to go in here. Come on. Select data. We're going to remove this one, and I'm going to add in data, right? The series name, we can call it just, we'll just put in the NACA name for it, right? And on our x-axis, we're going to want our alpha, or our angle of attack. And on our y-axis, we're going to want our CL. So we just click OK. Click OK again. You know, axis titles, alpha, CL. Right. So if we compare these side by side, let's do this. All right. Let's make this a little bit bigger. Put out of that. All right. If we look at our CL versus alpha graph, you know, this one's obviously much steeper. So you know, if I stretch this one out, something like this, right? We can see that they're looking identical to each other, right? So I know I graphed it right. I can match it within here. I can use this data for other things. Like, you know, obviously you may need some of the other stuff as well. It all depends on what you're trying to solve for, but you can use this data for other stuff. So let's say we're going to go to the folder. All right, so I can put the CSVs in there later. And let's go CD versus alpha. I'll just do them for all of them, just to show, you know, what we need to do. Insert CD, save file, save as, save. You go home, insert. Yeah, it's doing it again, so we'll just select data, remove it, add data, series name, the NACA. X values will be alpha again. Our Y values will be our CD, and we can click OK. Click OK again. So this graph, so XFLR5 over here. This is our CD versus alpha. So if we stretch this one out. It matches down here. Let's go to which other ones have I done? CL over CD. Insert C, Control V. This is going to be CD. All right, this one's a bit different, not alpha anymore, but still same process. Save, insert the smooth scatter. If you want, you can do just a normal scatter plot, or you can do ones that actually has the bullet points in it for the data you collected. I just like the smooth lines. It tends to just look a little bit better. We're going to do our X as our CL, our Y as our CD. Click OK. And the reason why we're doing this is it'll be easier for us to kind of visualize and double check our zero lift drag coefficient. Obviously, we're going to have to interpolate it a little bit because we have just below 0 and just above 0. So it'll be somewhere between these two values for our zero lift drag coefficient. And we can take that value and then look on our graph and confirm and visually confirm that we're kind of in the right ballpark. Click OK. It matches with the other one. Last one we have is the CL over CL divided by CD versus alpha graph. Insert Control C, Control V. This is CL divided by CD. Save file, save as, and we'll go insert. Title there, X values, alpha, Y values. Do that, right? And we can say that it's going to match. Check it with the XFLR5. All right, and it's this graph down here. So, yep, it's matching up. It's full screen all the different Excel sheets, so it's a bit easier for us. Okay, so now let's do some analysis using some of the Excel data that we have. I'm going to run through these real quick, at least the ones that involve doing stuff in Excel. So we did the plotting, right? So now we need to determine and tabulate lift curve slope. We're only going to be looking at one case. We're not going to be looking at all four cases. Angle of attack graph and compare these values with theoretical lift curve slope. So to do that, our lift curve slope for the wing, you have a wing, or CL equals a wing times alpha geometric minus alpha lift equals 0. You also have a wing equals a naught over 1 plus a naught over pi e aspect ratio. So we know what everything is in there, alpha or a naught is 2 pi, aspect ratio is 14, pi is pi, right? The only thing that we don't really know is what is E. So E is your span efficiency factor. I believe also like the Oswald efficiency factor. And to get that, you're going to consult this little graph right here to get the lowercase delta. So in this case, we have a taper ratio of 1/2, so it'll be right around here. And we have an aspect ratio of 14. So there's no 14 on here, but what we can do is if we zoom in as far as we can, right, we can just take the distance between 8 and 10, right? And we can estimate it, but we know that's a gap of 2. So if we take this and we go, right around there, and then again there, so like that's about, aspect ratio 14. And if you bring in that across to like here, right? Our efficiency factor will be, like, we'll say 0.015, right? Or sorry, delta equals 0.015. So that means we can solve for E. We can just take that value and we'll solve for E in here. Let's move this graph over a little bit. First, we can solve for E. We're going to set up E. We're going to do is equal to 1 divided by our delta 0.015 plus 1, right? And we get an E value. So then we can solve for A wing. So we just go AW, oh, not caps, AW, why not? And then this is going to equal, we're going to have, okay, 2 times pi. This is going to be divided by 1 plus, and take 2 times pi, divide that by pi times our E value, and we're going to multiply that by our aspect ratio of 14, and yes, we get A wing, and to double check it, we our theoretical, like the max you could get, would be a theory. This is just equal to 2 times pi. That's A naught, right? And A wing will always be less than A naught. We have a relatively high efficiency factor, so we're going to be not too far off from it. So that is our lift curve slope in the theoretical for the wing. Now we want to do CL versus alpha. We did that. So we want to do minimum CD for the corresponding angle of attack. Determine tabulate minimum CD. So let's go to our CD versus alpha graph. Let's move our graph out of the way. So we want to go just for the min CD, and we want to go alpha that corresponds with it. So we have just right now it's sorted with alpha being from smallest to largest. What we can do is we can say sort this from smallest to largest selection. Okay, right? It's obviously going to change our graph. We can fix that in a minute. But just for right now, let's go back to CD. All right, so we can now find our minimum CD value is this. It happens at -2 degrees angle attack. Let's see. Yeah, let's enter that, and then we can rearrange this back to sort small sort. All right, and it fixed our graph. Let's just clean it up. And we know from before our alpha was -2. This is degrees. If you want to do alpha in radians, you just take your -2, multiply it by pi divided by 180. And that's your alpha, or angle of attack in radians. So our next one is going to be determine tabulate maximum CL. So we're going to go back to our CL versus alpha, and we find that our maximum CL happens to also be at the maximum alpha given. So our max CL equals, first copy it in, and then alpha, this is 20, alpha, we'll denote radians for it, and we'll say this 20 times pi divided by 180. All right, so there we go for that one. Now we want to determine tabulate maximum CL versus CD. So we're going to go to our CL over CD versus alpha graph. Right, we're going to move that on over. And what we're looking at is just looking kind of on the table. We're going to be somewhere in the range of like 2 to 3, degrees, right? If we look right in our 2 to 3 degree range, we can actually see that our maximum CL over CD is that we got from XFLR5 is right there at 3 degrees angle of attack. So let's go max CL divided by CD and equal. We're just gonna do that, and then we'll do alpha. And we said this was at 3 degrees. We'll do alpha radians equals that times pi divided by 180. Nope, not 18. Let's add that 0. Right. So that's that one. Now we want to tabulate zero lift drag coefficient and the value of K. So to do that, we are going to go to our CL over CD. We want to find zero lift, so let's add some axis titles. The bottom side, or our x-axis, is our CL, and our y-axis is CD. So we need to find is our CD naught, or zero lift drag coefficient, which if you zoomed in on this graph, you could find it would be right around that point. But we can also do just do some interpolation again and figure out exactly what CD value we have. So we can go CD naught, tab over. We can do, it will be another big fraction again, but we'll do 0 minus this, our CL1 divided by CL2 minus CL1. This whole thing will be multiplied by CD2 minus CD1, and it's going to be all that is in, you're going to add CD1 to that whole thing. This is your CD naught. So kind of, let's double check that. Yeah, so let's not do that. So kind of right in between these two values, closer to the CL2 value. So this is our CD naught, and we now need to find our K value, right? So to find our K value, we know our equation, CD equals CD naught plus K CL squared. Well, we know CD, we know CD naught, we don't know K, and we know CL, and we can easily square it. So what we can do is we can then do CD minus CD naught over CL squared equals K. Right, we can just use some values off the chart or the table over here. So we can take, set up our fraction. We're going to take any CD value. We'll grab one just kind of out on the end. We'll go CD minus CD naught divided by your CL squared, and that will equal your K value. So there's our K value right there. Now we need overall induced drag, induced angle of attack, effective angle of attack, and downwash. So for this one, we're going to go back to our CL versus alpha. And what we want to do first is where we have our zero lift angle of attack. So to do this, it's some interpolation. So we'll go alpha lift equals 0. We set this up as 0 minus CL1 divided by CL2 minus CL1 times alpha 2 minus alpha 1 plus, wrong direction for that, plus alpha 1. Nope, and this is in degrees, right? let's shift these down real quick. Shift down. This is in degrees. Now, if we want to do radians, we're going to take this, multiply it by pi over 180. Right? There's our alpha zero lift angle of attack in degrees and radians. But we can also, because we're doing it at 5 degrees, alpha we'll do 5, and we'll do, drag that down, right? Got that. So this is our angle of attack. This is our geometric angle of attack. I can add geo to this if I want. Geo. So the other things we need to find is we need to find alpha I, CD I. Oh gosh, what were the other values? Alpha effective. Actually, insert some of this. Down. Alpha effective, CDI, and down wash. These two obviously won't have degrees or radians, so just insert yourself down. Insert shift cells down. So this will just be one table right here. Right. That doesn't need that. So to get our alpha I, what we can do is we can take our equation of the CL equals alpha naught times alpha geometric minus alpha I minus alpha lift equals 0. And we can, rearrange that, do a little bit of algebra, and set up that alpha I equals -1 times CL over A naught minus alpha geometric plus alpha lift equals 0. So if we do that, we can then do our CL, make sure it's at 5 degrees, divide this by 2 pi, and then we're going to subtract our alpha geometric in radians, and we're going to add our alpha lift equals 0 in radians. That gives us, this is in degrees. We're going to just redo that real quick. Just Control C that. So this is our alpha I in radians. If we want to convert it into degrees, we can just take this. We can multiply it by 180 divided by pi. Right? That's our alpha induced in degrees. Now, if you want to do alpha effective, it is just alpha effective is alpha geometric minus alpha induced. So we can just take alpha geometric, subtract alpha induced, and we can just bring it on over there. Now for CDI, our equation for this one is your induced drag coefficient is equal to alpha induced times your lift coefficient. So for this one, we can just take our alpha induced in radians and multiply it by our CL right here, and we get our induced drag coefficient. And for downwash, we get tan alpha I equals downwash over free stream velocity. And because we're dealing with small angles, we can drop out that tangent, and we can just get alpha I equals downwash over free stream. Bring free stream over, and you get downwash velocity is equal to our free stream velocity of 50 meters per second times our alpha I in radians, and we get our downwash velocity in meters per second. So our next one, at 5 degree angle of attack, plot the variation of local lift coefficient, local induced drag coefficient, local induced angle of attack, and local downwash. Let me write these down so I don't forget them. CL, CE, I, and omega. So let's go back to here. And for those, we have to go back to XFLR5. We have to go to this area right here. And I already have it set up, 5 degrees angle attack. You have alpha induced angle over span, induced drag drag over span, right? Because that's what it's saying. Local induced. So your local would just be at a specific point. Your local lift over span. And we also need our downwash. So let's change this. Current graph define. Oh, they don't have it. So we'll do the math for it then. Okay. So let's export. This will be, oh gosh, alpha I versus span. Save this. Export. This will be CDI versus span. This last one, export. This will be CL versus span. Right. So if we go back to our files, oh, wrong file section. Video files. There they are. So let's start with our alpha I versus span. So this right here, is our span. It starts at negative b over 2 and goes to b over 2, roughly. It's not exact. And then this right here is our alpha I. If you want to plot it, just plot, select that, add series name. Our x is our span, and our y is our alphas. These are all in degrees. Okay, so we get our graph like this. Okay, we just need to plot these. Yeah, and this is all at our 5 degrees angle of attack. So we have this one. Let's just save it real quick. Then let's go to our CL versus span. There it is. Insert. Just insert another chart. Select data, move it, add it. X value span. All right, this is our CL versus span. And let's go to the last one, which will be induced drag coefficient versus span, and then we'll do the math for the downwash velocity. All right, and that is our induced drag coefficient versus span. The last thing we need to do is we need to get the downwash velocity, right? And to do that, we're gonna have to just do a little bit of math, because we're going to need our induced alpha, right? And we know that we have a free stream of 50. We multiply that by our alpha induced, we get our downwash velocity. So what we can do here is we can do span, and we can do downwash. Just copy these in real quick. So our downwash velocity will be 50 times our alpha I, and the negative just will denote that it's in the downwards direction. Oh, first things first, we have to convert our alpha I's to radians actually. These are in degrees, and we need to do alpha I in radians, which this will just equal your induced times pi over 180. Just bring that all the way down. So now we can take our 50, multiply it by our alpha I in radians. We get our downwash velocity across the span. And what we can do now is we can actually graph this. We can select data, add, do this. Our x value again will be span. And our downwash will be this. Okay, you see the graphs look similar, just different scales for it because we multiplied alpha I by 50. So that's that one, and that is all the different Excel interpolation and analysis that we have to do. So thank you very much.